Howdy, and we're going to talk about Lab 16. So this is seismic interpretation, and this is going to help you understand why earthquakes of different magnitude, which is intensity, occur at very predictable locations a majority of the time. So plate boundaries are critical to understanding this lab. In your folder for Lab 16, you will find a map that shows the various different plates, lithospheric plates that is, across the globe. And when the arrows are pointing together, you've got some kind of convergent plate boundary. If you got them like this together in teeth, typically that reflects a subduction zone. So an ocean plate typically subducting under a continental plate. When you see arrows going the opposite direction, that's a divergent plate boundary. So there's two types. There's mid-oceanic ridges, MORs, like the Mid-Atlantic Ridge, where the crust is pulling apart in the ocean basin because of tension. You can see that on continents as well. For example, Iceland is a rift, R-I-F-T, and that's where two continent plates are pulling apart. Eventually, that rift will become a successful pulled apart continent if it doesn't fail. And if it does fail, it's called a failed rift. But when it doesn't, it's referred to and graduates to being a new ocean basin, which means we have a brand new MOR. Then there's the ones that move side by side. These are your transform boundaries that are things like strike slip faults that you learned about in faults and folds. That is a key thing for you to keep in mind as you're doing this lab. So think about subduction zones as we start this lab and realize that plates are diving into the subsurface, into the mantle. The angle of subduction will probably impact the intensity of an earthquake for most causes because you have so much bending, fracturing, and stress applied to the crust. So it's going to break apart, especially closer to the surface. So how do you do this lab? You're going to watch this video and you're going to read through all the instructions. And when you read through the instructions, then you're going to need to access the USGS earthquake map. USGS stands for United States Geological Survey. So let's take a look at the instructions here. You will notice that there's a disclaimer in question 3 because question 1 and 2 is very straightforward. I'm going over those now, and you're going to use the USGS webpage to research earthquakes across the globe at locations that I know that they occur. As you do this lab, I would like you to think about the focus of every earthquake that you research. So a focus represents the point of rupture of the fault where an earthquake occurs, and typically that's inside the earth. I often get questions, can they happen at the surface? Well, on a rare occasion, especially when you've got a shallow fault, maybe one that's just like a surface fault that's, just a couple of kilometers deep, sure, you could probably have that happen, even along places like the San Andreas. The big question is, how intense? What's the magnitude of these earthquakes? Because as you're doing your research, the depth of the focus should be a really important data point that you look at. Part 2 would be the magnitude. And then you're looking at where these earthquakes occur, not just geographically, but geologically in terms of along plate boundaries if they're not in a plate. So when they're not at a plate boundary, we call those intra-plates, meaning inside a plate. So that would be like you have a random earthquake in Waco, Texas. That would be an example of an intraplate earthquake because it's not at a major plate boundary anywhere in the world at this time. Most earthquakes that are super shallow, that have a focus of less than 10 kilometers beneath the Earth's surface, are typically associated with shallow faults that we can kind of refer to as surface faults. But when you get deeper ones, you're typically looking at some kind of either current or ancient subduction zone, or maybe even a very large mountain collision site. So you need to realize just because something's less than 10 kilometers does not automatically make it a fault that has a focus associated with a surface fault. Instead, you are going to have earthquakes that even along subduction zones could be very, very shallow, let's say right around 10 kilometers. But most on subduction zones are deeper, 25, 30, 40, 50, 60. They can get up to several hundred kilometers in depth. You would never have a surface fault that was that deep. It just wouldn't happen. You're looking at surface faults that just can't get that deep. They typically don't go beyond 10 kilometers. So if you had an unusual circumstance, here's the disclaimer. Let's say we're in Hawaii and there's a magma chamber that's 25, 50 kilometers beneath the Earth's surface, and that's producing magma plumes that are working their way up towards the surface, creating earthquakes as they get into the volcanic pipe and up towards the volcano itself. Then that might be an exception to the rule that you'd have a deeper earthquake focus. So I wanted to talk about that. As you do the lab, you need to realize that every question matters. So I'm going to go through this, and you need to hear the different components and how you do this lab. So question 2 is by far the most important one, and it's going to be the biggest bang for your buck in this lab. So make sure that you answer all the locations that I've given you across the world. Once you finish, it's required that you save this as a single PDF and not submit pictures of every page. That's a real easy thing to do, and I'm going to demonstrate in just a second what you can do. You can take this, and you can take each picture, if you're doing it that way, and just put it into a document, like a Word document, and do a save as to a PDF, and that puts it in one document. That allows me to grade it much more efficiently. All right, so once you've read all of this and you understand that process, the next one is to write a hypothesis statement. This is where students have the most trouble in this lab, because they really think that a hypothesis has to be accurate in every aspect. So let me just kind of get this out of the way. Science is all about proving or disproving a well-founded and crafted hypothesis. In true scientific research, you would hit the scientific literature and research in advance. So you have a very strong and good hypothesis statement based on prior scientific work, and usually you're reproducing that work or taking it to the next step. We're going to start with the basics of making a hypothesis statement. It needs to be a statement that is clear and well-founded with geologic evidence to support it with your knowledge thus far in the course. So that means like plate boundaries. So here's what I'm asking you to do. You are going to identify 3 specific localities, geographic sites, that exist along major plate boundaries in the world that are prone to producing magnitude rated earthquakes that are 7.0 or higher. So that's going to be a major earthquake, a great, or rare great. So now that you know that majors are 7.0s to 7.9 magnitude, greats are 8.0 to 8.9, and rare greats are 9.0 and higher. Just to reiterate what you learned in lecture, it is an open-ended scale for magnitude. So the highest rated one at the date of this recording that's been measured is the one that was the rare great earthquake of 9.5 in Chile, South America in 1960. Let's hope we don't get one larger than that. But the problem with these types of earthquakes is the rupture zone can be very large. So if you get a subduction zone, that can be 100 kilometers, 500 kilometers of distance where a large area is ruptured. So the intensity of the shaking is huge in magnitude, and typically the time frame lasts a long time in earthquake terms. So anything that's more than a minute is a long time for an earthquake. So here's what I want you to do. It doesn't matter if your predictions are proved wrong in science. What we do is use data to drive us to conclusions. Because oftentimes what we think about the earth is really not what it ends up being. So that's why we get out and do scientific research. That's kind of what you're going to do today. So the scientific method is what you're going to use, and I need your hypothesis as a starting point for this lab. When you do this, you want to provide scientific reasons why you think your predictions are going to be correct. For example, I'll just throw out one that everyone would normally choose along the San Andreas Fault. They say, okay, that's going to be a place where a majority of the earthquakes that are 7.0 and higher in magnitude occur. Well, why? It's not just because it's in California. It's because it's along a major transform plate boundary that is moving, and you would want to research how that plate is moving. Is it moving in a northeast, northwest, southeast, southwest manner in relationship to the North American plate? You can easily find that information. So you're choosing 3 sites. That is okay, but be specific. So if you just say something like Japan, China, North America, South America, that's not cutting it. It needs to be specific. So are we talking about Mongolia? Are we talking about Beijing? Are we talking about Tokyo? Are we talking about Waco, Texas? Are we talking about San Francisco? And then I want you to identify the plate boundary where it is. So that is super important. So give your scientific evidence and reasoning. Once you do that, you'll be moving into the chart that is where you're going to fill out all this information. So question 2 is the largest question of the lab, and you will need to use this map that I'm fixing to show you and how to use it, and look for all of these places. Southern California along San Andreas Fault. I didn't give you a GPS location. I gave you general areas because typically earthquake can occur along any of these areas over hundreds of kilometers. And then you're going to continue on the next page. There are 15 of them. You will find the focus depth, the magnitude rating, and yes, the modified Mercalli rating if provided on the USGS site, and I'll show you where to find that. And then you're going to put a fault description. So if it's a subduction zone where this occurred, let me just use an example. You've got one in Japan. Well, Japan is along a major subduction zone. You get a continent-to-continent boundary. Let's say one occurs in Turkey or Afghanistan. That would be a good example of a continent-to-continent location. You get one along a transform plate boundary. That's going to be one like the San Andreas Fault. You get one along a divergent plate boundary, which would be something like a continental rift or a mid-oceanic ridge. Then you get one that's an intraplate earthquake. These are ones that occur within a continent, not along a major plate boundary. All right, so let's take a moment to show you the USGS webpage. The way you can find this is to type in USGS earthquake. All right, so now that you have this map up, what does all of this mean? Let's first look at the colors. So you'll see different colors on these maps, and typically the red ones are ones that are the most recent. When you get into the legend, you can see what red and orange mean, but the size of the circle matters. So the size is going to be the larger the earthquake. Let's just compare. Here's a tiny one. This is Hawaii. And when I pull it up and I put my mouse on it, notice it said an M. That's a magnitude of 2.9. Gives you a location of where it occurred, so 29 kilometers west-southwest of a certain place in Hawaii. This little thing right here, the Roman numerals, I think is important because that's your modified Mercalli rating of damage. So many earthquakes do produce some type of damage, so they'll get an assessment there. And then your focus depth is this part right here. So 15.8 kilometers. And your location, here it is, and your time of when it occurred. Everything's done in universal time. So if you want to learn more about this earthquake, just select the blue information, and then you can learn a lot about it. For example, you can see the magnitude, its focus depth, and you can get into its rating. And here it is. Here's your modified Mercalli rating. And you can come in and see where it was and where the potential damage would be. This is on the Big Island right here. This is an interesting earthquake because this one happened on the northwest side of Hawaii. Most of them are down here. Point being is you can even get information about tsunamis in this location. So when you're in the map, let's say you have questions and you get to a point where you're like, well, I can't find it. Go back to the menu or hit your back button. If that doesn't work, open up another browser, type in USGS webpage, and then a good place to answer all your questions is about. So come here and it will give you everything you need to know about how to use the application. Another great resource is the wheel, because you can actually set your parameters to use this application. Instead of just looking at the last day, you can look at the last 7 days, a certain group of earthquakes that had a magnitude of, let's say, 4.5 and higher, 2.5 and higher, or you can do all magnitudes in the last 7 days. Same thing. You can look at the last month. You can even go beyond that by doing a very detailed search of older earthquakes. So note there saying, oh, well, there were no earthquakes in the last 30 days. You need to use the application and find one that's maybe a year old, because all of these places have earthquakes on a regular basis. And then you can use the universal time, or what they're calling user time, but it's actually universal time, and do kilometers in your distance. And then you can install this on your desktop and actually get notified when an earthquake occurs in those locations. There's actually an app for your phone. So when I did that, a lot more earthquakes came up. You're like, well, what's the yellow? So that's where the legend comes into place. So now that I've done that, I have way too many earthquakes. So I may want to go back in and I may want to filter some of this. So I'm not going to do everything in the last day. What we'll do the last let's just try last 7 days, all magnitude, last 30 days, or 4.5 and higher. You can see, oh, we get new ones with white colors. What does all of this mean? So use the legend. You always need to use a legend when you are working with some kind of application. And that's easy to find when you're working in this thing to figure out. So let's say I'm going to make this a little different. Let's just do 4.5 in the last 7 days. And I'm going to start poking on things. So this is along the Aleutian Trench, which is a subduction zone where the Pacific plate is subducting under the North American plate, right along Alaska and in between Russia, this area. So let's just click on this and notice it brings up a magnitude of 5.6, the location, and then it says, oh, okay, there's the shake map, there's the IV is the modified Mercalli rating, and oops, look at here, we got something interesting there. No tsunami warning. That's interesting. So sometimes your earthquakes will generate tsunamis. They're typically in ones that are fairly large, like in the ocean, that are around 6.5 or higher. So let's look at this one right along South America. And this is in Argentina. Notice there's no tsunami. This would be your tsunami warning here, green. And here's your modified Mercalli. Here's your focus depth, your location. So each one of these you should be opening up and getting all the information out of it. Now, this is where you can kind of see information that will help. So you can also look at ground failure, if there was any mass wasting that occurred. So the map tells a bunch of information about these earthquakes. So what you're going to do is, if you don't know where a location is in your lab, you need to do a geographic search for it. So I have some all over the world. You have some down here in New Zealand. You have some over here along Japan. I have some along the San Andreas, some up here, some in Hawaii, South America, along this area. And here's Iceland up here. You can move your map this way. So there's a lot that you can do with it. And if you want to change the way this looks, if you want to do terrain, which I kind of like, you want to use a satellite view, that's also cool. You can add in more stuff. You could add in U.S. faults. That gets interesting when you start adding in these layers of information, because they help to give you more detail, granular detail to why earthquakes matter. So let's get back to your lab form. You go through all of these places, and you're going to go to 15 of them. And I just mentioned where some of them are. Let's say if you don't know where Sumatra exactly is, just do a research for on a map, like a Google map, and you can find every single one of these places. All of them are going to have earthquakes on a regular basis. But the goal is that you're trying to find these pieces of information: this focus depth, the magnitude rating, the modified Mercalli rating, which was the Roman numerals, and you assess the fault description. It's not going to give you that. This is a big part of the lab, is you correlating what type of plate boundary that each of these locations are associated with. Once you do that, you're going to come to question 3, and you're going to look at the data you collected, and you're going to rank them with the highest magnitude. Number 2 would have the next highest. Number 3 would have the third highest of your 15. 4 would have the fourth highest of your 15 sites, and 5 would have your 5th highest. Then you're going to rank your 5th lowest magnitude earthquakes. And same thing. The lowest one goes as number 1, so forth. Your top highest, your top 5 lowest. Once you do that, you're going to be, on each of these questions, you're going to discuss why you think this happened. Was there a common theme between where your highest magnitude occurred? Did you have them on all types of plate boundaries? Did you have them predominantly at subduction zones, or did you have them predominantly in intraplate earthquake situations? Same thing with your lowest magnitude. Now, on number 5, you're going to look at your table from question 2 and identify which sites had the highest modified Mercalli scale damage in Roman numerals. And you're going to discuss the correlation between those highest modified Mercalli intensity rating scale assigned values, and then talk about, okay, let's look at the focus depth of that, and also correlate that to magnitude. And then think about the population of that area, what kind of human structures, like buildings, if there needed to be special building codes, if you see a really high modified Mercalli rating, and so forth. So when you do that, once you get to 6, then you're going to get into just a small amount of math. This is a super easy question. People get kind of concerned about this. It's like, oh, math. All right, so if you'll just follow the instructions, what we're going to do is try to triangulate where an earthquake occurred. And earthquakes, in order to do that, to find the epicenter, you've got to have at least 3 seismograph stations, but there are hundreds across the globe. So you're going to look at the first P wave arrival time and the first S wave arrival time, and you'll just do the math of the difference between the two. So for this one, this was started at 7 a.m. for the first P wave, and the first S wave arrived at 7:33. So that's 33 minutes. So come up here and follow the instructions. I gave you an example, a theoretical one that had an arrival time at the first P wave at 9:20 and the first S wave at 9:32. So that's 12 minutes. And then you're going to use this calculation of 8.4, which is just the standard calculation to convert this to distance. And that's going to equate, you're going to take 12 times 8.4, and that gives you 100.8 kilometers. Use this process right here, that same map, 8.4 times whatever minutes you got for each of these Alpha, Bravo, Charlie, Delta, Echo, and Foxtrot. And you're going to put them here. And the one that ranks as being the closest, meaning the closest to the epicenter goes as one, the one that's farthest away goes here. So they may or may not end up in the same order that you have them listed here. All right, once you get into number 7, you're going to take the data from your research and you're going to evaluate. This is where you start to go back and you're thinking about your hypothesis statement. You're going to look at your highest magnitude ratings and cite each example from the data you collected in this research, meaning from the USGS map. On number 8, I want you to think about if you had a magnitude earthquake of 8.5 and a focus depth of 15.8 kilometers and it occurred along the Juan de Fuca plate, which is subducting right along the North American plate where Oregon and Washington state are in Northern California. And it has a focus depth of 372 kilometers. Explain why you think that that one would be different than the same exact earthquake rating with one that's 15.8 kilometers. So you're going to compare a shallow versus a deep earthquake with the same magnitude rating and the same location. Now, let's go back to thinking about your hypothesis in number 9. So you're going to revisit your hypothesis question and you're going to identify your 3 sites again. And then you're going to look at the top 3 earthquakes with the highest magnitude ratings. And you're going to evaluate were any of those the same. So basically, you're looking at your data that you collected versus your hypothesis. Then you're going to reevaluate your hypothesis. Where were you accurate? Where were you not? This is not about being right. This is about evaluation of your data. That's all we're doing here. It's okay if your information didn't turn out to be correct. Your data drove you to new information. That is the lab in itself. So when you get to the point where you're working with the map, remember the reds are the most recent. Then you can get into the yellows and the oranges, but bigger circles represent larger magnitudes. Little ones represent smaller magnitudes. And it's interesting to just work in the map for a while. Thinking back to the map, make your settings, okay? And remember to click on each and every earthquake. That gives you the data that you're going to use. So if you decide you're going to use this one right here in Honduras, click on it and get all the data because there's so much behind the scenes, not just this one map with a bunch of dots on it. That's it in a nutshell. Remember, when you complete this, even if you are taking, let's say you get back to your lab and you are doing pictures with a phone of your pages, or you use a snipping tool. If you can see my screen here, I just typed in snipping tool on a PC. And I can just take a screenshot of my entire page. And what I could do is open up, when I finish, a Word document. And you have these applications for free from the college that you can download. And you can put it right there. And once you're finished, put all of your pages there that you completed, but make sure all the information's there. Do a save as, and make sure you know where you save it. But this is where it's important. Label your document with your name. And I would put Lab 16. And then come down where it says Save As type and do a PDF. And then this thing will automatically convert to PDF in one singular document. PDFs work with Brightspace. So I can always open them, but when people turn in pictures, sometimes they turn them in, oftentimes actually, in a format that cannot be evaluated in Brightspace. I'm so excited for you to do this lab because once you start working with the USGS earthquake map, it's pretty darn cool. And you put the app on your phone, you're going to be like, oh, that's really awesome. And you will get notified when earthquakes occur and where you want to know they are. Let me know if you have questions, but don't start this lab an hour before it's due and expect that you're going to get it done. You need the full 3 hours of lab in a week to do this particular assignment, and you'll be glad you did. Thanks so much for your time. Bye.